Wemachola pumentulongweni ndinengxaka zomsi wam uyeyo hayo ha ndinengxaka zomsi wam wemachola pumentulongweni ndinengxaka zomsi wam uyeyo hayo ha ndinengxaka zomsi wam.
This is David Van Vranken, and I want to welcome everybody to our 26th and final lecture in Chemistry 51C here at UC Irvine during the fall of 2020. I ran into one of my colleagues, Felix Grun, in the parking lot on the way into work, and he runs the UCI mass spectrometry facility. And I stopped by their laboratory where he works with Benjamin Katz. Felix and Benjamin, it's kind of like they work in Disneyland with unlimited use of the attractions. And one of the things that they were doing is that they were isolating extracts from plants in order to characterize the composition of those plants. And so let me give you a little bit of the backstory that I got on what's making, what's leading them to do that. So it turns out, I hope all of you have had a chance to visit the UCI Arboretum at some point, because there's this area of the Arboretum that has all of these plants that are from different parts of the world that are usually come from similar environments to Southern California, like South Africa or arid types of climates that are similar to ours. But they're getting ready, if I understand correctly, they're getting ready to bulldoze this over in order to make a staging area for construction of the new UCI Medical Center clinic that's going to be on that north edge of campus, what's called North Campus. And so if you're interested in these plants, you have a very limited time to see these plants. Some of the kinds of plants that you see there are different types of aloes, but one of those interesting plants that Felix mentioned was this plant that they had there that's commonly referred to as Bushman poison bulb. And how can I not talk about that at the beginning of our class? Because everything about that seems interesting. You can see this very interesting plant, and there's this tuber on the bottom there that's quite massive. Let's take a closer look at this plant. I'm not exactly sure how to pronounce this, the scientific Linnaean description, whether it's Boophone or Boophone. But this is Bushman poison bulb, which is common to South Africa, the southern parts of the African continent. And here's a picture of it growing in the wild in a more native habitat. But that bulb on the bottom has this papery layered structure. And if you cross-section that, you can see all the layers with that pulpy stuff inside of there. And traditional healers and medicine people make extracts of that. They make decoctions of this root material, of this tuber material. And they use it for various purposes at great risk, I would say. Here's a section that I found from a book on ethnobotany.
Ya salí, mami. Pero ya estoy en clase otra vez.
Okay, I'm gonna have to
I'm in
mute.
class again.
I'm gonna have to mute here because that's going out on the. Okay, so one of the entries that I found describes this Bushman poison bulb and some of the uses or misuses. In rural districts of South Africa, at least 30 deaths from Boophone poisoning are known in 1 year, and the same applies to Zimbabwe. The true incidence of fatal Boophone poisoning is certainly higher. Such poisonings are based mainly on medical use as a remedy against gastrointestinal troubles, abdominal pains, or general weakness, but often too on the use as an enema to drive out spirits. It seems to me like there are some sorts of potentially medical uses for this Bushman poison bulb, but it's also very toxic. So in this book description, they have a composition, a typical composition of the alkaloids that are present in that root bulb. Alkaloids are nitrogen-containing organic compounds, natural organic compounds. And the one that is most abundant in this African version is bufanedrine. And it has anti-pain properties, analgesic properties with an effective dose, a 50% effective dose of 6.2 mg per kilogram. but that's very close to the dose that you need for lethality to kill mammals. The therapeutic index for this is razor thin. So how are you going to dose up enough of this compound to cure your pain, but not so much that you cause half of the population to die? That's the real trick. Now, does Boophone have the same composition of alkaloids when it's grown in Southern California? Who knows? I guess Felix and Ben are going to figure that out by running samples in the mass spectrometry facility. Very interesting plant, and boy, you would have to be really hard up to want somebody to treat you with this, with some sort of herbal remedy that's based on Boophone. Okay, let's come back to our lecture here. We've been reviewing material that you might see outside of our course. How can you use the kinds of reactions that you're learning about inside of our course in future courses that you take or on standardized examinations? And so we're just trying to practice using the tools that we've been learning in this course. We have our final exam coming up on Friday. That's in a couple of days. And I want to encourage you to practice your problem-solving skills as much as you possibly can, because that's really what I'm going to test on. And even if you feel like your grade won't be what you want, give it everything you've got, because wherever you're going after you take this class, you're going to need those problem-solving skills. And if I see you after this course is over, again, I don't judge you in any way based on your grade in my class. Your grade in my class does not define you. I'm just so happy that you signed up for my class and took my class, and that we had a chance to talk about and learn about organic chemistry together. So keep going with that. Let's keep practicing here. Here's some questions that were on the Princeton review of the medical college admissions test exam. And it's clearly, this question is an aldol reaction. The formatting of this is a little bit different from what we've seen, and you just have to be ready for that when you walk out of our class. I gave you a very specific rule that said you can kind of see that there's no alpha hydrogens on this benzaldehyde. So this is a formula for an efficient crossed aldol condensation. So they're showing this as a 1-to-1 ratio because they haven't written anything additional, so you have to assume it's 1-to-1 ratio. So they're trying to do a single aldol addition, and the reaction will not stop at a single aldol step. So there's an intermediate here, and I think they're telling you to show this initial intermediate that you get before the elimination reaction. But I told you a specific rule for our Chemistry 51C course here at UC Irvine, and that is that if you have a chance for extended conjugation between this substituent and the carbonyl, then you'll undergo a spontaneous elimination. Whereas here, in this question, they're assuming that you have to do an acid-catalyzed elimination of water. But let me go ahead and draw out what you would get after this. What you would get after this step is you would get the enone. This would be the product. And you'd get an E and Z mixture of this, of the two different alkenyl isomers as the product for that reaction. So according to this, according to the question, the way they phrased it here, they're implying that you need H plus and heat to affect the elimination. But again, I gave you a specific rule for our course where I told you that if you have an opportunity for conjugation, the elimination of water will be spontaneous under the conditions of the aldol reaction. Okay, there's another reaction down below here, which is clearly a directed aldol reaction. And again, I want you to notice that one of these two components has no alpha hydrogens on it, right? On this side over here, there isn't even an alpha carbon. So of course, you can't ever deprotonate directly next to the carbonyl. Only carbon atoms, you can deprotonate carbon atoms that are next to carbonyl. So there's only one place to deprotonate here. And in practice, you would treat this substrate down below here, this one to the right, with LDA, let it form the enolate quantitatively, and then you would add the aldehyde. That's the more typical way that this is run. You wouldn't run it the way they drew it here, where you mix everything together and add LDA. So you're clearly going to generate an enolate on the less substituted side. That's what we learned about in this class. So let me go ahead and just sketch that in. Here's where you're going to form the enolate using the LDA, and that's going to react with the aldehyde, and it's going to form a bond. Let me go ahead and draw the arrow pushing for that. Right, that enolate is going to form a carbon-carbon bond there, and so the product that you get from what's shown here, according to what they've shown, there's no workup that's been shown here. So this would be the product of that reaction, and there would be a lithium counterion to that. I think presumably they meant that you're supposed to follow this up with an aqueous workup. But if I don't show you the aqueous workup, this would be the product you would have to draw. And I hope you recognize that this would be a mixture of two, I forgot that isopropyl group. This would be a mixture of two stereoisomers. Sorry. Actually, there would be four because we create two new stereogenic centers. Let me highlight those. Wow, this is complex. So I'm just going to highlight that there's two stereo centers. That means there's four possible stereoisomers, two stereo centers. Right? You could have RR, RS, SS, SR. And I would expect you to draw all of those, but I wouldn't ask this question because I don't want you to have to draw four different products for the reaction, or otherwise I would say don't worry about stereochemistry. Okay, so enolate chemistry. You need to know enolate chemistry. That's why you're taking this course, and I hope you remember that when you leave this course. I took this this tiny little section of the tricarboxylic acid cycle, the citric acid cycle, from one of my colleagues' notes, Professor Pavan Karandale over in biological sciences. And the citric acid cycle, I remember that I had to learn that back when I was taking biochemistry as an undergraduate. And I just feel like they never told me why that was useful and how it relates to organic chemistry, which is quite sad because the chemistry in the citric acid cycle is just a lot of interesting stuff. All right, when you draw out the chemical structures for these substrates and you look at what's going on in this reaction, it's enolate chemistry, just like we've been learning in this section. What's going on in the enzyme active site in order to make this next intermediate citrate, that's this down below here, that's citrate, right? Once you draw out the structures of the enzymatic intermediates, you can tell that what's going on here is that this is an aldol reaction. That's how you make that carbon-carbon bond. That's what citrate synthase is for. Citrate synthase catalyzes an aldol reaction, just like we're learning about in this course. So it's too bad that they just use the names and they don't draw the chemical structures and talk about the chemistry that's going on in these reactions, because when you draw all the intermediates in that citric acid cycle, just really interesting chemistry, and almost all of it comes from this quarter of organic chemistry here at UC Irvine. Okay, so here's a question that came from the optometry school admissions test. The tests, whether it's optometry or dental school or medical school, they tend to have very similar types of questions on there. And in this question, they're asking you something about enolate formation. They're asking you which hydrogens can be deprotonated. And to me, this is just screaming at me in terms of the which one is the right answer. So first of all, let's go ahead and draw out these possibilities. HA, could you ever deprotonate? We have never, ever in this class, and we never will draw any reaction that leads to an acyl anion, where a carbonyl is deprotonated and has a negative charge like that. We've never made those. You don't know how to make those. I don't know how to make those. There's no such thing. It's not stabilized by anything. So there's no way you would ever get this. Let's go ahead and take a look at this other position. And that's over here where you remove proton B. So if you remove proton B, that looks fantastic. That's an enolate. So let me just write yes. Let me put an exclamation point there. That's yes. And the reason why this is so stabilized and so easy to deprotonate is because we can draw a resonance structure for this that looks like that. Let's go ahead and draw out the arrow pushing for that. That carbonyl is accepting that electron density, so it makes it very easy to deprotonate at that position. So of course we can deprotonate HB. Finally, we'll come down and look at HC. And HC and HD are the same, are indistinguishable. So, you know, position C and D, maybe they're just trying to trick you there to see. I mean, if you didn't pick HC, why would you pick HD? But this is just these protons over here. If I'm going to draw everything that's on this carbon atom. If you deprotonate out here, it's completely unstabilized. You might as well be just deprotonating butane or hexane. That's completely unstabilized. So I'll just put no, you can't make that carbanion. There's nothing about that. So really, it's HB that is the answer for this question. That's the one that forms the enolate. And after you've taken 2 chapters full of enolate chemistry, I would expect you to be able to easily answer this question. So correct answer here is B. They're not all the same acidity. And then these 2 are indistinguishable. I'm not sure if I can fit that in here. Indistinguishable. I'll just put indisting to kind of abbreviate that. So yeah, so you need to know enolate chemistry when from our class. Okay, here's a reaction that when I look at this, I cannot help but see this pattern of oxygen atoms with a 1-3 relationship, 3 atoms away from each other. That tells me it's an aldol reaction, or I could probably make that through an aldol reaction. And which bond? This bond. I've practiced enough aldol reactions that I know that this is the bond that you make by adding an enolate to a carbonyl. So let's go ahead and work a little bit backwards here and try to see how that would work. So if I work backwards, you know, it looks to me like I could make that if I deprotonated this carbonyl compound like this. I'll draw the H so it looks kind of like the starting material. And then I added that to another carbonyl. And this time, instead of drawing the ethyl up, maybe I'll draw it down again. I think we might have, I feel like we've drawn out this exact reaction before somewhere in our notes. I'm not sure. But this is readily identifiable at this stage for you because you just finished covering a couple of chapters on enolate chemistry, and addition to carbonyls should be readily identifiable as an aldol reaction. So which of these answers corresponds to this reaction? So we'll go ahead and take a look here at these different possibilities. Here's one possibility, and I'll try to draw out those and see if they match the answer that I drew. The first molecule is acid aldehyde. Well, that's not the right set of structures. The other one is another aldehyde that has a propyl group at the end. That's not going to give the right pattern. If you form a bond here, or if you did it the other way around, you wouldn't get the right structure. So really, the right answer for this is going to be this. So I'm just going to put an X through that. Okay, let's go ahead and look at B. So B looks to me like it's acetone and acid. And again, you can arrange these so that either one can form the enolate. I'll arrange it like this, but these 2 are not going to combine together to give the structure that's drawn below. You're right. So one of these is butanal again, and acetone, and one possible pattern of combination would be like this. That's not going to give the carbon backbone that's shown below. The other way, in theory, that you could have combined those together, those same 2 molecules, I didn't show the 2 combinations up above, would be to add to the ketone, and that just does not seem plausible. Let me, I've drawn one too many carbon bonds there. So there's acid, there's the aldehyde fragment, and then the ketone fragment would be here. And again, if I made a bond here, that's not going to give the backbone that's shown up above. So let's go ahead and cross that out. That's not right. Let's go ahead and take a look at this third example here, the C, and what are those pieces? Those pieces look to me like it's an even more complex ketone. Almost, but not quite right. So one of them looks like this, but there's a methyl group on the other side, right? We need an aldehyde on the other side. And then the other possible combination is pretty close, right? This is pretty close, but it's got one. If you just count the carbon atoms, there's no way this could lead to the right product. It has the wrong number of carbon atoms when you count them up. So let's just cross that out right off the bat. I'm looking at choice D here, and that's looking pretty promising. Boy, I'm running out of room here. D. Let's go ahead and draw those out. That's exactly the combination that I showed you up above. this is going to be the right answer. It's propanal, a 3-carbon aldehyde with another propanal, and that's looking pretty good there. That's the one that's going to lead to the product that we, so that's yes. We could stop right there, but let's just go ahead and convince ourselves that the last one, that the last one there, I'll just refer to it over here as E, that is not going to work. And it doesn't matter how I arrange this. This is not going to give the right number of carbon atoms. If I just count the number of carbon atoms, there's 1, 2, 3, 4, 5, but the product shown over here has 6 carbons. Let me draw that 6 a little better. So that can't possibly be the right answer, something where the reactants only have 5 carbons. So you have to practice the Aldol reaction over and over in order to be good, and to be good enough to where years from now, potentially, if you're taking one of these admissions tests, that you would remember how to work through these types of problems and work backwards, really. Here's a question that came from the Pharmacy College admissions test, and it's asking you to characterize amines. And I think I've mentioned that amine nomenclature is different from the nomenclature of carbocations and of alcohols. So let me go ahead and draw examples of each of these types of amines. So type A is called a secondary amine. That's when you have an NH and 2 alkyl groups on there, R and R prime. Type B is called a quaternary ammonium salt. That's where there's 4 bonds to nitrogen. And if I have 4 bonds to nitrogen, there has to be a positive charge somewhere. I can already tell that answer B is the right answer for a quaternary ammonium ion. And then C is talking about a tertiary amine. That's when there's only 3 bonds and you have a free lone pair there. And then part D is asking you about a primary amine where there's an NH and another H and then a single R group on there. And there's a lone pair there. So really this species that they've drawn using this typesetting corresponds to answer B. That's a quaternary ammonium salt. It is not an amine. It is not a base. It's a salt. And they're not specifying what the counterion is. Okay, here's a really bizarre species that we haven't talked about in our course, and it is called, there's no way you could have answered this unless you read other parts of the book other than what we covered during our Chemistry 51C course. Let me go ahead and draw out more clearly what this structure is. It's a phenyl group attached to 3 nitrogens, and it looks like this. It's kind of like an ylide. Remember the phrase phosphorus ylide. And there's another resonance structure that is commonly drawn for that. Here's another resonance structure that is commonly drawn for this species. And again, we're going to have 2 charges on here. There's no way to draw this functional group without having charges on it. This functional group here is called an azide. And I'm not sure if is it only our textbook that doesn't discuss the chemistry of azides, or is it possible that maybe I missed this section of the book? I don't think so. But it's not a diazo compound, which we didn't discuss. It's not a urethane. Let me draw examples of these. So urethane A, a urethane is a carbonyl group with nitrogens on both sides. And I'm not quite sure that we discussed those types of urethane derivatives, but you can see there's no carbon-carbon bonds in a urethane functional group. Right? The carbonyl has heteroatoms on both sides. B is a diazo compound, very similar to an azide. We didn't discuss the chemistry of diazo compounds. But a diazo compound looks a little bit similar to the azide, except it's carbon, nitrogen, nitrogen. And it looks like that. And then compound D, so this is, I'm going to go ahead and circle C, that's the answer. A nitrile, that's really the only functional group that, after taking our course, that I expect you to know. This is a nitrile functional group, and R can be whatever alkyl group you want. So we typically cover, for sure, diazo compounds, oh, you know what? I've missed, boy, I am so glad I looked at this carefully. The first one, that's not the right structure of the urethane. A urethane has an oxygen on one side. Oh, my brain is a little bit spaced out here. So that's a urethane, sorry. It's a carbon that has no alkyl group, no carbon-carbon bonds in it, but one side has oxygen, the other side has nitrogen. that other thing I had drawn is referred to as a urea. Okay, so yeah, so we didn't talk about this functional group, but I'm just trying to get you prepared. Sometimes you're going to run into questions where we just didn't cover that part of the book. Okay, I included a section in here because I find that the chemistry of positively charged species is very confusing, and I want to try to resolve that. I have a lecture from last spring that was posted online that discusses this in detail. And the challenge is this. You've now seen 3 types of positively charged ions based on second row atoms. You've discussed carbocations, and this is the carbocation that you learned about. You've discussed ammonium ions, and this is the type of nitrogen cation that you've learned about. And you've discussed cations based on oxygen, and this is the kind that you've talked about. It doesn't matter whether it's a protonated carbonyl or not. And what we never told you, we never mentioned this, we didn't make any big deal about it, is these actually come from 2 completely different classes of cations. There's 2 classes of cations, and that's what makes everything so confusing. One class of cations, one family, is called enium ions. So this species here with carbon is called a carbenium ion. We didn't tell you that. We only told you carbocation. We didn't tell you there's another species of carbocation called a carbonium ion that has 5 bonds to carbon. You may have thought that you can't have 5 bonds to carbon. The answer is, of course you can. You just can't have more than 8 electrons. And this is okay because this has only 8 electrons. As long as you don't violate the octet rule, you can have 5 bonds to carbon. So you're never going to see this unless you go look at the way they process petroleum derivatives in the petroleum industry. This is the way they crack long chains of crude oil into short chains of gasoline or petrol. So it's not that carbonium ions don't exist, it's just that we haven't covered them. And we never mentioned there were 2 families. We've talked about nitrogen with a positive charge. We've talked about ammonium ions. There's another type of nitrogen cation that we never mentioned, and you're never going to see, and I've never seen it before, called a nitrenium ion. It's kind of like a carbocation, but based on nitrogen. And we would call that a nitrenium ion. And these are so unstable, they just don't exist. And they're not important intermediates. I'll just write DNE for does not exist, and it's too unstable. And if a nitrenium ion is so unstable that it can't exist, there's no way you're going to form an oxenium ion. So again, why didn't they mention it before? Because these things are so unstable that they're only just kind of speculative hypothetical intermediates. So you're probably confused because the carbocations we taught you about come from the enium class. They're carbenium ions. And the ammonium and oxonium ions we taught you about come from the onium ion class. And one of these can be attacked, right? I have no problems coming over here and attacking this, right? You know the carbocations, but you can't attack these other ones over on the other side because they already have too many electrons. You don't try to attack these. You're misthinking you're confusing the reactivity of enium ions, which want to be attacked, with the reactivity of onium ions, which already have too many bonds. So that's why it's been confusing for many of you, is because we've confused you. We didn't tell you there were 2 families of cations. And I apologize for that. The book should have made that clear at the very beginning. Okay, and I think this is our last problem. This comes from, again, from the Pharmacy College admissions test. This is stuff that we've covered in our chapter on organometallic reagents, chapter 20, and in the amines chapter. And it's if you take benzamide, so let me go ahead and draw out the structure of benzamide. It's a derivative of benzoic acid. Wow, this is kind of like a nomenclature question because you have to know that benzamide is a derivative of benzoic acid. This is benzamide. And the question is, what happens if you treat this with lithium aluminum hydride? And they're not mentioning the aqueous workup. There has to be an aqueous workup after this. I hope you know, after we've covered our course here, that this is going to reduce down the carbonyl to a CH2 group. That's what happens for amines. You don't cleave the carbon-nitrogen bond. So the expected reaction after, and let me put it in parentheses here, H2O workup. They didn't mention that. So step 2 should be this simple amine compound, and the name of this is benzylamine. That's the right answer, and that's the one that should be in that list. So let me go ahead and come over here and circle that benzylamine. What's the first one? Well, whatever is A can't possibly be the right answer because there can't be 2 right answers on this question. So A is benzoic acid. And so there's no way if you treated benzamide with lithium aluminum hydride that you're going to get benzoic acid. So that's just plain wrong. Let me just cross that out. The answer B is benzonitrile. It doesn't matter whether you know whether it's a benzyl nitrile or a phenyl group directly attached to the nitrile. There's no way you're going to directly reduce an amide and get a nitrile out of that. That's just plain wrong. And then finally, the last one is ammonium benzoate. Boy, I don't think we really discussed the naming of salts. A benzoate, that ate ending tells me it's derived from benzoic acid. And there's a negative charge, right? Tetrahydridoaluminate, there's a negative charge on aluminum. Cuprate, there's a negative charge on copper. Benzoate, there's a negative charge on the benzoic acid anion. Acetate, there's a negative charge. So benzoate is benzoic acid with a negative charge on there. And it tells you that the counter cation is an ammonium ion. And I think you guys know what an ammonium ion is from general chemistry. An ammonium ion is just N with 4 bonds attached to it. So that's ammonium benzoate, and that's definitely not the right answer here. You're not going to get ammonium benzoate by doing a lithium aluminum hydride reduction. That's what you would get if you hydrolyzed benzamide under as the neutral salt species. Okay, that's it for our course. And once again, let me say thank you for participating in my course. I'm super thrilled that you come and learn about organic chemistry together with me and my team, Jason and Matt and Thao, and thanks for participating.